Hello, student. Welcome. After watching the review videos on functions and other college algebra and pre-calculus level topics, this is the first lecture on the proper syllabus of the course Finite Mathematics that you are undertaking. Um, the, although it is the first topic, you see section 1.4 here. That's because I have adapted the slides for my video lectures from Finite Mathematics with Applications published by Pearson and the authors Goldstein and others. In that book, in the 12th edition, in chapter 1, this is the topic in section 1.4. Okay. And these slides should also be available either on your learning LMS platform or in the description of the YouTube video. Please make sure that you take notes, have this downloaded or printed and take notes as you are watching the video. I said this in my introduction videos as well, but I would like to repeat, at least for the first proper video for the course. Okay. What is the method of least squares? The method is you want to develop a model for some data that you have, right? For example, I'll just put it in abstract sense for now. You are measuring some quantity against time, let's say, maybe some profit earned in a year, by your company, and you have the different or in the different months of 1 year, and you have these different months plotted on the x-axis, and how much profit you made, every month. That data you make like that. And I'm being optimistic, you started in the January, and in the course of the year your business grew and you're making more and more profit. And suppose the data was like that, in some months there was some slump, maybe there was inflation and people were not in spending as much and so on, and then you have this data, let's say, for 12 months or 24 months, however long you collected it. Now you would want to know how much profit I will be making in this business 5 years down the line, or 2 years, 3 years down the line, right? That is a very realistic situation. How would I get a reliable prediction? You would plot this data and you would think, what if I try to find a line that fits this? Because that's the best fit there. The word here is best fit. Okay. And once I have this line, okay, my choice color, the choice of my color was poor. Okay, I need to choose the pink one. And over the once you find a very good line fitting that data, you can use that as a kind of your prediction. That's your model, and you can then extend that further, and now you can on the time axis, the horizontal axis, you can make a prediction for the future. Why would it make sense to do this? Because this is the line which is the which represents the fluctuations going on with the data in the best way, right? For example, I cannot assume that my profit is like that. Doesn't make sense. My profit is here. That line is deviating away. I cannot assume my profit is going down. Doesn't make sense. It's increasing. What is the best fit here, right? That is the line that I want to get. And how would I know which line is that? That's where the method of least squares comes into picture. What is the least square that you will get off? You will measure, now I'll zoom in and show you. Okay. From here, this is the line, on the line, I have circled it here. That is the value predicted by the line, by your model, and that's the actual value. Okay. Now, what is the difference between them? You know, we call it x minus xi, let's say here. Take that difference x minus xi, which is the height of that vertical distance, and you square it, because sometimes the error will be positive and sometimes the error will, like, the difference will be positive, sometimes it will be negative. If you don't square it, they will end up canceling and you will lose the meaning, right? We don't care whether the um, difference from the actual value is positive or negative. We want to know how much different it was, right? So you square it, and after you square it, you add all those vertical distances squared, because they represent by how much, your model prediction is different from the actual values. And what do we want to do? If you want your model to be good, you want those differences to be as less as possible. Okay. Least square, method of least square comes there. All right. um, I drew a straight line here as my model, and that is where it is used most often. But I should also tell you that in theory, you can use any other model also. Okay, you could use the least square with a quadratic model or a exponential model, because the underlying theory is the same, right? To minimize the error between the predicted value and the actual value. Okay, let us now run through the contents of the slides. What's the outline here? What is the least square problem? We will go through that again. And what is the error? I spoke about that error, right? The difference between the actual value and the value predicted by your model. Then, of course, we'll talk about the line, and we will also talk about, we will not be doing it, but I will talk about, using technology to get that. In fact, your calculator, the Texas Instruments calculator, um, you have to watch some YouTube videos to learn that. Okay, it gives you the least squares line if you plot the data points. Okay, all right. So here are the data points. This is the theory. Okay, suppose you are observed these data points and find the straight line that best fits these points. Okay, that is the goal, right? How do we do? We look at the error. When you say best fits, the errors is minimum, right? And the least square, so what we do, we take the errors, square them, as I said, so that we don't lose the distinction, we don't cancel the plus and minus errors, and then take the sum. Now, what is your goal? Minimize E. No, that will be our goal. Okay. And here is an example of calculating the errors with some model. Okay. Determine the least squares error when that line is used to approximate the data point this. Um, there's a little correction I would say in the wording used here. Let's not say least squares error for now. You can say it, but I mean, in what you have to understand what you are saying. Okay, so okay, let me not correct it. Let me put that in a parenthesis. For now, let me say determine the error when that line is used to approximate these points. Okay, now this is trying to again reinforce and develop properly the idea of least error. You have these points. I'm just randomly plotting 3 points, and you are given some line, right? Then you can take that line and find these vertical distances and square them and add them, right? The sum of those values will give you an idea about how good that line is fitting those data. If my line was something like this, I would get more errors, right? Large error because these values would be very huge. That is a basic logic here. Okay. So right now, we don't know whether this is the best line. What I'm getting at is we don't know whether that is the best fit line. We are saying let us take this line and find what the error is. Okay, with that line. And what is the technique? Take the data points and then take the corresponding point on the line. This is the very important part for you to understand. Okay. Now, what is corresponding point? I will show you the calculation for one of them. Take x equal to 1, right? Now, you have to visualize the coordinate axis. I will try to do some justice here by drawing a small diagram. Take x equal to 1. The actual data point at 1 is somewhere here. Let's say that is 6. So 1 comma 6, that's your actual data point. Okay. But what does the line, the model predict? Okay. Predicted by the model. Predicted by the model, the value is 1.5 times 1 plus 3. Right? It's 1.5 x plus 3 and x is 1. So that is 1.5 plus 3, 4.5. So the value predicted by the model is 4.5. It's here. Okay. So for this data point, the error, the amount of error is this difference, 1.5. From 4.5 to 6. Okay. The height is 1.5. That is the amount of error at that data point. Now you are going to square it. That 1.5, you'll square it, it will be 2.25. And repeat this for the other points. Okay. At 4, plug in x equal to 4 in the equation, you get 1.5 times 4 plus 3. Now 1.5 times 4 is 6. So 6 plus 3, 9. Okay. So the point on the line is 4 comma 9, whereas the actual point is 4 comma 5 given point. Okay. So the difference is now 9 and 5. The difference is 4 squared. Like that, right? Then you repeat for the other point. Now you have these squares of errors in the last column here. You take their sum. So the total squared error is 22.25 with that line. And this line would be the best fit line if that is the minimum you can get. You know, if there is no other function, no other line which will give you error less than this, then this is the best fit. Otherwise, it is not. So our goal is to find what line will minimize this. And you can see now you can already see the problem is at the outset it's not trivial, it's not obvious. Okay, there has to be some method that you have to develop, right, to come up with a formula here. Okay. This is the graphical illustration of what I was talking about. Of course, this is more neat and clean. Take a moment to see everything clearly. Okay. The error 1, error 2, error 3, all of them are given there. And okay, here's now the formula. Right, I was saying it's not trivial, and you can see that the formulas are not trivial either. Okay, so I'm boxing them here and highlighting them. I want you to make note of these formulas. So when I say make note, it's there on your note taking guide printed, but you don't be satisfied with that. Write it. Okay, take a on a piece of paper or on the same note taking guide in the back side and the corner. Just try to memorize and write it. Okay. Now, what is the formula about? The formula is like direct, it's once you like have the formula with you, it's direct. Okay. So you want to find the line. The equation of a line in slope intercept form is y equals mx plus b. M is the slope, b is the y intercept. The formula gives you those values, m and b. Okay. Let us understand the formula. What are the quantities in the formula? That is another, of course, when you want to actually find the least square line, that is the most important part, right? How to use the formula. So n is the number of points you have. So in our case, the previous example, n will be 3. There were 3 points, right? What would be summation xy? For that, you have to look at the data points. Okay. Remember, you don't have the line with you right now. Don't confuse with that line 1.5x plus 3. Okay. We don't know the line. We don't know the equation of the line. The only thing we don't know the equation of the least square line. We only have the data points 1, 6, 4, 5, and 6, 14. So x and y are those things 1, 6, 4, 5, 6, and 14. Okay. Then when we say x summation here, xy, that is the product xy here. So you would multiply them 6 times 1, 4 times 5, and 6 times 14. Okay, that is 1684. Okay. And what is sum xy then? Summation xy is the sum here. Summation xy will be add this 110. 6 plus 20 plus 84. I have been saying that, but in case if you didn't know, that notation here, this sigma that you see, okay, is the capital sigma in the Greek alphabet, and it's the summation notation. Okay. Whenever you see that notation, basically means you add, right? Take the sum. So sum of what? All the xy values. So summation xy means that all of these values minus sum of x times sum of y. So we need these sums also. Sum x is 11. We can check that. Sum y will be 11 plus 14, 25. Okay, so we have the value of summation xy. We have the value of summation x, summation y. So the numerator in that formula, everything is known. What is in the denominator? I'm going to erase a couple of stuffs here so for clarity. Okay. In the denominator, you have summation x squared. That's okay because I have summation x 11. So you just need to whole square it, 11 square. Okay, that part. That's fine. The other term is sum of x square. See, that's the difference. Okay. There is a difference between writing sum x whole squared and sum x squared. The one on the left is the sum of all x's, 11 in this case, that you are squaring. Sum of x square on the other hand is, first you have to square the x values and then take the sum, which means our table is not complete. There's one more column in the table, x square column. 1, 4 square 16, 6 square 36. So when you take the sum here, it's on the very right corner towards the bottom on your screen. Okay. Sum x square equals 16 and 36 is 52 plus 153. Okay. So that is the value 53 you plug in the formula here. and that gives you the value of m. Similarly, the value of b, now first you need m. Okay, that's why in the formula first you compute the m. Then to compute b, take summation y, which is known 25 here. The value of m you have calculated just now. Summation x, we know it, and is the number of data points. Okay, that is how formula is. And here's that table, much more better print, of course. Okay, uh, we did calculate these values earlier. Looks like we were correct in all of them. And now applying the formula. First calculate m approximately. Okay, now you want to round up, that's approximately 1.45, and then use that 1.45, or use the not the approximate value, use the actual value. Okay, in that formula there, right? Summation y minus m summation x over n. Okay, then you get the value of approximate value of b, and you plug in the equation. So that's your list, that slope and that y-intercept. Okay, you have the y-intercept and you have the slope. You can plot the line. All right. Remember the approximate equation. Sorry, the equation that you had taken earlier was 1.5x plus 3, I think. Okay, 1.5x plus 3. Now, if you see the actual best fit line, this is close, I would say, not actually the best fit, but close to it. Okay. So our error was not that bad. The actual error might be a little less than 22. What did we find the error there? It was 22.25. The least error could be 20 or something, less than that, a little less than that. Okay. All right. Before moving on, there's one more thing I wanted to highlight here. See, in the formula, you had the 1.45 calculated for as the value of m, right? But when we wanted to use m in the calculation of b, we did not use 1.45. That's important in calculations. Okay. Why? Because that 1.45 is already an approximation. And if you use that to calculate the b, first of all, we'll already have to do some approximation for b also, because there will be some decimals, And on top of that, if you have used a value that was already an approximation, you're compounding the error. If you want to note down the terminology, okay, that will compound the error. The error will get added. So take the exact value of m. So what did we take? This is the exact value. This is the approx value. So we use the exact value whenever possible in intermediate formulas. Okay, bear that in mind. Okay, the method is as simple as that. There isn't much to discuss. Okay, here's a thing about using technology. So one of them is the Excel sheet itself. Okay, if on the Excel sheet itself you can find the least square, apparently. Okay, there should be some function to do that. Honestly, I'm not that good in Excel. Should not be a very difficult thing if you do some Google search or ask an AI model. Okay, how to do it. But it's a good skill. I'm not discounting it. My goal is to focus on the conceptual part of it, and which I do. But of course, like in today's world, we are not going to do everything by hand, right? We're going to use technology. You need to have the understanding, the mathematical understanding, because then you know what you are talking about, you know what calculation you have done, and you know what you have obtained, so you can interpret it, right? But we should also be um, familiar with technology wherever we need. Okay, now if you are working, many of you might already be knowing how to do this. Otherwise, you will learn, okay, when it is needed. If you want to learn it for your exams and that you do for this course, welcome, okay, and you can use the calculator and get the answers. And in fact, I might ask some questions to just do that. Okay. Here's a summary. The method of least square finds the line that is the best fit, for the collection of points. The vertical distances are the errors which we square and add and try to minimize. This is a finite mathematics with application course. Okay, so as you might have expected, we don't do the proof, like that formula was given. Don't ask, how did you come up with that formula? Again, it's not super difficult. A little bit of calculus can produce that, but that's not what we do here. Here we take the mathematical results and apply in most cases, okay? But we develop the understanding of what it means and how to use it. So we're done with the lecture part of this video. In the next video, I will be solving problems on this topic. Okay, see you there.